Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture video 15, or lecture 15, and we are covering sections 6, part 6 and 7 of chapter 3, and we are completing an example for the balanced fixed effects one-way ANOVA model. Before we get started, I want to talk about this RMD file that you have that I've posted for you. You will change the title when you do a problem, whether it's homework or a project. You will change the title. Obviously, you need to change the author to your name and the date to the date that you have completed the assignment. Then do not change anything in output, including down to here. If you change this, some of these settings are settings that I have researched in order to get the file to knit at the end. At the end, you need to knit here, and we want to knit to PDF. So let's see what happens when we do this. You'll notice that down here, we've gone from console over to R Markdown, and we're going to get a percentage as we go through, and then the messages from these libraries. Please do not change the library chunk nor the setting chunk. Leave them as they are. These are some good practice, because especially here we have some code that if it's removed or altered, you will not be able to knit your file as a PDF. You will have an error. And so we've gotten past the 100%. We get to this knit, the .md. That means that we shouldn't have too many errors. And there comes the PDF file. Okay, so this is how the file should look when you're done, and this is what you'll turn in along with your RMD file for both homework and for projects. All right, so we've done this. We've done the first part of this example in previous videos, so I'm going to jump down to where we're going to start for this video. At the end of code lecture 2. So what I'm going to do is come down to this chunk, and before we start, and I'm going to say run all chunks above. It will not run this chunk of code, but every code or every chunk up until here. And you're going to see the same initial down here in the console, even though you just saw it on the knit. It did that in the compilation of the PDF document, not in the environment. We didn't have anything here until I just ran code. So knitting the document does not run the code in the same way. All right, so now I need to find where we were. Okay, when you do this, it changes your position, because that's why I have the line numbers over here, so I can make sure that I get back to the same place. When you start adding output, it changes your position of where you were, so you need to find your position again afterwards if you're trying to come back to the same place. Okay, so we're going to talk about confidence intervals for treatment means. We could call this confidence intervals for treatment effects, and we could do that by solving the equation mu I equals mu plus tau I for tau I. So what we would do is we would take yi dot bar minus y dot dot bar, and then use the same margin of error, the same plus or minus, if you will, for the confidence interval. And we could do that, but we'd have to do that manually. I don't know of any code that does that automatically. In fact, I've had to write my own code for quite a bit of this, as you'll see. Okay, which is going to make it a little challenging for you to change, and I apologize. When you're using predefined functions, it's a lot better. So let's get started. We have the treatment mean estimates from table 2 R. So previously we ran the favstats, and we obtained mean, standard deviations, some quartile information, etc. for each of the treatment levels. All right, so I have broken these up into math environment sections that are small, so that it won't affect the wrapping of the text depending on your how much text you have. So this first part between these two dollar signs just gives us the set of the mu I. In this case, it goes from 1 to 4. Now, because we've had only 4, I can say 1, 2, 3, 4. Okay, this is the one time, if you're going to list out the means, you have to list them all out. So if you have 10 of them, you would list all 10 of them here. I don't suggest that you do that. In that case, I would change this to say the means, treatment means range from blah, blah, blah for the, the minimum, which is the blah, blah, blah for such and such treatment level, up to whatever it is for whichever treatment level that is. So we can make this a little bit shorter if we have, let's say, more than 5 of these. Okay, if you get too many, you don't want to have to list them all out, and they already have it in the table, so you can reference the table like I did here. Okay, and so we've got this, and then we've got equals. Here's the values in another bit of, so we had mu hat, right, equals, and then we have the y, 1 dot bar, 2 dot bar, 3 dot bar, 4 dot bar, and then in the last one we have the actual values that show up. And then the overall mean for the experiment is, and here is y dot dot bar. Okay, so now we're going to say that the individual 95% confidence intervals for each treatment mean are provided in and I say table 3C below. So I've written, even though we have a function here, I've made them look nice and put them in tables for you. So then you have to say something about them. What do you see? So this is going to change based on your particular problem. In this case, none of the confidence intervals overlap, and indicating that our treatment variable, power level, has a significant effect on the etch rate, our response variable. So you have to modify this to be specific for you. And then I say the interpretation of individual confidence intervals are provided below. So I give the code here, and the code is pretty easy. You would need to change this inside the AOV function if you were doing a different problem, obviously. And then you would need to change your treatment variable, specify what it's named. It has to be, it's case sensitive, so if it were, let's say, weight, and it was capitalized in W-E-I-G-H-T, it would have to be spelled properly and match up what you had in your data frame, right? Okay, and then p-adjust equals none. Okay, this is an LSD dot test. That means least significant differences. And what I found is that I don't see any difference in anything by changing this to Bonferroni or anything else. So I don't know if, let's see, I don't remember. Maybe it changes the critical value. Oh, maybe it changes the p-values. I'm not sure, but when I was looking at this, I couldn't notice the difference between changing it. So you can try that on your own if you like, but I won't ask you for that for these individual confidence intervals for treatment means, okay? And then you can change alpha if you like. Okay, well so let's run this code. So here's model, and then here's the LSD, and oops, oh, why didn't it print output? Let's see, so okay, so it output now. So, oh, because I didn't tell it to output, that's why. So I just ran the code, I didn't tell it to print the object. So it breaks it up into statistics, parameters, the means with their confidence intervals, and some quartile information, and then something about comparisons are null. So I guess because we didn't put anything in there to specify the comparisons. And then the etch rate. So this is telling us groups. So it's grouping 220 level is going to be considered group A. And so the groups that are the same as group A are just A. So none of the other groups, none of the other power levels, because you can see this says groups, so it's saying that instead of levels, it's calling this groups over here, the 220, 200, 180, 160. And so the first one is always A, and it's telling us the mean etch rate for that group or that level, and then it's saying that it is the same as itself, nothing else. If the confidence intervals overlapped with anything else, those letters, B, C, or D in this case, would show up right beside A. And the same thing for B, it's only with itself. And C is only with itself. And D is only with itself. That means each of these do not overlap or cannot be considered the same as any of the others. Okay? And so up here we have the actual confidence interval, the lower and the upper control or confidence limits, yes. And we see the max, the max here, 568 something, is below the min of the next one, and the max of the next one is below the min of the next one, and the max of that one is below the min of the next one. So there are no overlaps, and that's what it's saying. Okay, so these are the confidence intervals here, and I've got a t-value of 2.12 about. I'm not sure what this means. I thought it was coefficient of variation, but I don't think it is. And I am not sure what they mean by LSD here. Maybe they're changing this to an F value or something. I'm not sure. But there's not a lot of documentation on the help page for this function. I've put these into tables and explained the things that I know to explain, but some of them I just didn't know how to explain. Okay, so if we change this to Bonferroni, has 2 R's, I believe, yeah, 2 R's. Okay, so Bonferroni, it's not capitalized. I'm looking at the help for this. Make sure you spell it right. So now I'm going to run it and see if I can see what's different, if anything. Okay, so yes, so what changed is the t-value, the critical value, but it should have changed the confidence intervals because it has a new t-value to multiply by the standard error, but it didn't change them, and so that's why I'm leaving this as none and suggesting that you don't change this here. This way you have the unadjusted and it's printing out what you have actually calculated here. All right, so again, these packages with these functions are designed by people and they really aren't double checked by anyone. So we have to be careful using R to make sure that what it's good to do some manual verification the first time we use things to make sure that it's printing out what we want. So here I've given you the first table and specified what we have, but then the things that I don't know, I've just left until I can figure out what they stand for. And then the second part, for parameters. And then table 3C, you see here, is the one I referenced. This has the unadjusted confidence intervals in there and some other information. Standard deviation, the mean etch rate, I should change that. Okay. So here are our interpretations for each one of these. So depending on what the question asks, you're going to have to interpret one or more of these confidence levels. So you do that here. And I've given you the verbiage for each one of these. We'll just talk about the first one. We are 95%. Of course, if you change to something different than alpha 0.05, you need to change this to 1 minus that. We are 95% confident that the interval from the lower value to the upper value contains the population mean etch rate for wafers produced in this process. We have to be specific. It's not for all wafers everywhere. It's in this process, specifically at this manufacturer, specifically at this manufacturer's, on this manufacturer's equipment or production line, whatever is specific to this experiment, that's where we have to be careful. So produced in this process using 160 watts of RF power. Again, what are we changing the level of? And the interval was calculated using N1 equals N equals 5 observations. Again, it's important to tell us how many observations are in there. If there were 50 in here, I would have a lot more, I would know that this confidence interval had a lot more power to detect the true population mean not being in the confidence interval. Okay, so the higher the sample size, the higher the power. We've set alpha. So alpha is not, the type 1 error is not going to change. It's the power that will change by the um, sample size. Okay, and so I do that for all of them with all of their individual information. So instead of making you do that, I've provided it for you. You can just modify it. Now we have some miscellaneous info that you're going to have to change based on the problem to make sure that this does what it's supposed to do. And then I have this chunk, so we'll run that chunk. Then I have this chunk here. I have an include equals false and an echo equals false. And what this does, the include equals false means that the output is not printed. So I run this chunk and nothing happens down here. Okay. That's because of the include equals false. I say echo equals false, and that means when you knit this or compile it, this code is not going to show up in your document either, in your PDF file. So if you want to use this, instead of using this, then you would comment out, so you would put the include equals false and the echo equals false up here after the name. You'd put it right there. And then you would remove it from this chunk here. You would remove the comma all the way out to the bracket. Okay. So I have run the code, but I have not printed it out because I ran the whole chunk. And if you run the whole chunk, it honors the settings that you have up here. If you don't run it from here, or by running all code or what have you, then it will not take those settings into account, so it'll just print it out. So here is 95% confidence intervals for mean etch rate. You'll see they're the same except rounded to 3 decimal places, and it doesn't have all the other information. Okay, so and I should say, let me change it while I'm thinking about it, 95% unadjusted confidence intervals. All right, so that we know what we're looking at, unadjusted, not controlled for experiment-wise error. So here we come with simultaneous confidence intervals for difference in treatment means. This is also known as pairwise contrast. So I wanted to put these, I think the book confuses these two, the confidence intervals and the contrast. The confidence intervals of a difference is a contrast. So I just want you to know that they're the same thing for these pairwise differences. Anytime you're taking a difference between two means in an ANOVA or a regression, you are doing a contrast. Okay, because you're taking one minus something, or some of those means minus some other of those means, and setting them equal to 0, that difference. And that is a contrast, okay? A difference or contrast. So we are here, I've put this down below, I've run this code. And once I run this code, and I have 3 ways to run this code. I'll talk about that in a minute. You want to use as many simultaneous as few simultaneous confidence intervals at once that you can. So there's I've set this up so that you can change the code. The first one puts 3, 4, 5, all 6 that are possible in this case. Okay, and this data will have to be modified, and so this may take you a little bit. So give yourself enough time to tweak this code, because it is a little complex. Okay. It's just tedious is what it is, but it's easy to make a mistake. It took me a while to get the errors in the number of parentheses and commas in the right spot, and the C binds and the R bind in the right spot. It's just a little tedious, but I'm happy to help you during office hours get this. I can coach you through this, and then hopefully you'll understand what you've done, and then you can do it for yourself the next time or on the project. Okay, so once I've done this, I have this table down here, and in this case I just want to know if any of them are different in sequential order. So if y1 minus y2 is not the same, which it's not, because both the lower and upper confidence limits are both negative. That means 0 is not in the interval. And then between 2 and 3, the same thing. 0 is not in here. And between 3 and 4, 0 is definitely not in there. That means if 1 and 2 are different, 2 and 3 are different, 3 and 4 are different, that means that 3 and 1 are certainly different. 4 and 2 are certainly different, and 4 and 1 are definitely different. Okay, so that's one way to look at it, because if these consecutive ones are all different, then any other combination is certainly different. I've used the A-1 independent confidence intervals here, so they don't overlap or repeat, or they're not redundant with each other. In this first part of code, PRWS, so pairwise 1, I have a lot of redundancies. I have 1 minus 2, 1 minus 3, 1 minus 4. By itself, that is enough. So if they're all different, you can certainly say that if these are different, then you certainly know they're not the same as the first level. None of them are the same. So if you went to 2 minus 3 and 2 minus 4, then that is beyond the A-1 independent. It's no longer independent of these up here. Okay, those are dependent upon each other, or overlapping, if you will. And then 3 minus 4 is going to be overlapping with these others, 2 and 2 minus 3 and 1 minus 2. Okay, so this is all possible ones in the first one, when you have 4 levels. And then the second one, this is again just talking about, let's see, 1 to 2, 2 to 3, and 3 to 4. And then the third one is here, we're just doing, I'm sorry, 1 to 2, 3, so that was 3. 2 is just doing 1 to 2, 2 to 3, 3 to 4. And 3 is doing 1 to 2, 1 to 3, is that different? Yeah, okay. And 1 to 4. So what I've printed out is pairwise 2 here, but in the, I've chosen it. As you can see in the code here, I've got it highlighted, and you can see that pairwise 2 is changed. So if you don't want to use pairwise 3, then change this, and this, or not here, but in the code, you can change these 3 to whichever one you want. They have to be the same, or else you're going to have a mix-up. So you want to make sure that if you chose pairwise 3, 3 for all of it. If you choose pairwise 1, all of these have to be pairwise 1. Okay, but pairwise 2 certainly tells us in this case what we need to know. And I've done the write-up for each one up here. We're 95% confident that the interval contains the population difference in the mean etch rate between 160 and 180 watts. And I put it in the order that it is because we're getting a negative, and we know that mu of 160 power level is smaller than mu of 180, so that's why we have a negative. And then this is 180 minus 200, this is 200 minus 220. Again, if you change which one of these you use, pairwise 1 or 3, then you need to change, you'll have a different write-up up here, so you'll need to modify it. All right. Now, the Bonferroni method. Now we're going to adjust for the falsely inflated experiment-wise error, not falsely, but undesired inflation of the experiment-wise error that we have by doing simultaneous confidence intervals. So these up here are unadjusted. Now we're going to adjust for experiment-wise error, and so we do that by we have to change this code to how many simultaneous confidence intervals we want. Okay, so if you want 3 of them, A-1, you change it to 3, and then whatever alpha is here, it does the rest of the calculations for you. This has to match up to what you want. So I have done 1 here, which is y1, y1 minus y2, y1 minus y3, y1 minus y4, all of them, all 6 again. So bond CI1 corresponds to pairwise 1 above. And then 2, here's 2, this corresponds to 3 above, I apologize. And then 3 corresponds to 2 above. But they're not really related because just so you know, because you would only do one of these. You don't, unless it asks you for the unadjusted and the Bonferroni, you would not do both. You would do only one of them and comment out the others. Okay. So here under the Bonferroni method, again, I say that we replace alpha over 2 with alpha over 2 times r for r, and you would say, let's see, for r equals 4, and so you would say, then you could say alpha over 2 with alpha over 2 times r, which is 4 in this case. And so we're going to perform 3 simultaneous confidence intervals to determine if there are any differences in mean etch rates at different power levels. I only need one period. And so here's the first one. We are 95% confident that the interval from here to here contains the population difference, that means the true actual value of the mean etch rate, difference in etch rate between 160 and 180 for the power levels for the wafers produced in this process again. The interval was calculated using N1 equals N2 equals N equals 5 observations in each power level. So again, you'll have to change this as well. And then we have the others listed. So then we have a conclusion. In conclusion, the difference in mean etch rate for all power levels are significantly different at an experiment-wise confidence level of at least, and this is the safest thing to say, at least. So if you have equal sample sizes is equal to this. If you have unequal sample sizes is at least 95%. Okay. All right. And so you'll see that R is 6 here for all of them, and then for the other two I have R is equal to 3, and alpha R is here. Now this is redundant, so actually I'm going to remove that. You only need it one spot. No, I didn't. I put it all 3 places so that you have it just one place to go to. You don't have to change it in all 3 spots. There's more than one spot. Okay, so it's all together. And so again, for these other two, we use R equals 3, which means that 1 minus alpha over 1 minus alpha dot R over 2 is bigger than it would be for R equals 6. Or actually, this is bigger. And so 1 minus this is smaller, or let's see, yeah. So if this is smaller here for R equals 3, so then this overall 1 minus alpha is going to be bigger than it would be when R is equal to 6 up here. Okay? R is equal to 6 makes this value bigger. That's right, makes this value bigger. So this value is bigger. I was backwards. For R equals 3, this value is smaller. So this, yeah, so, okay. I'm really messing this up. I'm sorry. So when R is equal to 6, this value is bigger, so this value is smaller. Right? 1 minus that is smaller. When R is equal to 3, this value is smaller, so 1 minus that value is bigger. Okay. All right. And so, well, I thought I'd run this. I guess I didn't, did I? So we'll run this chunk, and again, I've put it in a nice table, simultaneous 95% Bonferroni adjusted. That tells me the method, not just that I adjusted for the experiment-wise error, but that I used the Bonferroni method. Okay, and we see that there's 3 confidence intervals, and none of them contain 0. What I would like to point out is that you see this interval, it goes from -67 to -5. This one is -60 to -11. So this is a smaller confidence interval, and in this case it's further away from 0. So for the unadjusted, it's easier to reject the null hypothesis because the interval is smaller. For the Bonferroni, it's more difficult to reject the null because the interval is bigger and therefore more likely to contain 0. And so if you have too many of these simultaneous confidence intervals at once, then, of course, if they're simultaneous, they're at once. All right, then these intervals get so big that it's almost impossible sometimes to reject any of the hypotheses, the null hypotheses about this. Okay, so we're going to test for differences in mean. These are hypothesis tests, and so we're testing that mu I minus mu j is equal to 0 versus that it's not equal to 0. And then we go for I equals 1 to whatever A is. Okay? at an experiment-wise confidence level of at least 95%. Again, that's the safe way of expressing this. The confidence level of at least 95% shows that there is sufficient evidence to support the claim that the mean etch rate for power level is different than that of the others using n equals 5 observations for each power level. Let's take a look at what I mean there. So all I get here is the test using the Bonferroni. So I've used the LSD test using the Bonferroni P adjustment. Okay, so the mean is not going to be different, but the confidence levels should be. Okay. Then we have Tukey's method, and the confidence intervals from this method are between the length of the unadjusted and the Bonferroni adjusted in length when the same number of confidence intervals are calculated for both the Bonferroni and this Tukey. Okay. When we only calculate A-1 confidence intervals for the Bonferroni method, we see that the Bonferroni method will produce a shorter interval. Why is that? Because remember, Tukey's method do all possible pairwise, not just the ones we select. It does all possible. So it's going to give us all 6 possible pairwise comparisons here. Okay, so if you were using a Bonferroni method for all 6 confidence intervals, then the Bonferroni method would have longer intervals than the Tukey method. But because we used R equals 3 in this case, the Bonferroni method will produce a shorter interval than the Tukey method. Okay? So the Tukey method, when you're comparing apples to apples, or the same number of simultaneous confidence intervals against each other, then the Tukey is less conservative than the Bonferroni. But if we control the number of confidence intervals for the Bonferroni, then that could be actually less conservative than the Tukey method. All right, so it just depends on the situation. All right, but in general, again, comparing apples to apples, the Tukey method is less conservative than the Bonferroni. So if we're comparing the same number of simultaneous confidence intervals, the length of the confidence intervals for the Bonferroni are longer than those for the Tukey. But if we're not comparing the same number of confidence intervals for both, then the Bonferroni may not be as conservative as the Tukey, which is the case here. So, but you just have to look at it to see which situation you're in. All right. So we'll run this code, and it gives us a nice picture. But so this is using Tukey's method, so we can see. But unfortunately, it doesn't. Let's see if I can. Do I have plots? Did it plot it? No, it didn't. So it's interesting that it doesn't send it over to the plot here. Whoops. And then we have here the differences for each of the means. So we can look at the order of this and then know in our plot which one's which. So they match up. They're in the same order. Okay. So when we look at this, we have the confidence interval, and then we have the adjusted p-value for Tukey. Okay. So we can perform hypothesis tests. We don't have the test statistic, but that's okay. We can just not include the test statistic in the write-up and just say about that the calculated test statistic not shown in parentheses corresponds to a p-value of 0.029, And if we're using confidence intervals, we have the confidence intervals here. But this is reversing it from what I did. This is taking the second level minus the first, the third level minus the first, the fourth level minus the first, the third minus the second, fourth minus the second, and then the third minus the, or fourth minus the third. Okay, so they're all positive because we took a bigger number minus the smaller number. Okay, and none of the confidence intervals contain 0. They're all of these numbers for the lower are above 0. So 0 is not in the confidence interval. So we can talk about each individual confidence interval, and then in conclusion, we need to say something about all of them together. The difference in mean etch rate for all power levels are significantly different at an experiment-wise confidence level of at least 95%. Okay. So now we talk about multiple comparisons. So those were pairwise contrast. Now we're going to talk about here's a pairwise, here's another pairwise, and now here is a four-way comparison. So I could write this as a contrast, and here is how we write it as a contrast. So we have the positive, positive, negative, negative coefficients. Okay, so if you're going to create a matrix for this, it needs to be in this format where they're set equal to 0 so that you get the right coefficients. If you try to use this formulation, then you might think they're all positive ones, and they're not. Remember that the coefficients have to add up to 0. So it's better to write this in this method, in this manner, so that you have the contrast and you can easily see how you should write the matrix. And so here is the contrast matrix. For the first, I'm doing 3, so this is 3 minus 4. So that means that the first C1 is 0, that goes with mu1. C2 is 0, that goes with mu2. You have to put the place level in there so that it knows that those are 0, and then that the third one is 1 and the fourth one's negative 1. And then I think I have these mixed up, so this one, yeah, so which ones? This is 3 and 4, and I didn't write 1 and 2. So this last one is that mu1 is equal to mu2, or mu1 minus mu2 is equal to 0. So we've done that, we've put that up earlier, but I didn't repeat it here. I should, so I will do that quickly. And the mu1 minus mu2, mu1 minus mu2. Okay. So there's the 3. So here are the contrasts defined here. We have to run this code. And so then we run this code, and I've got mu34, that's the name of it, is equal to C1. I have to give it a name, how I want this to print out. Mu12 minus, or mu12 underscore mu34. This tells me, when I read this, I know I'm talking about mu1 plus mu2 minus mu3 plus mu4, or minus mu3 minus mu4 for C2, and then mu1 minus mu2. If you want to change this, it has to all be one connected thing of text. So however you would like to do it, you can expand this or use the same or what have you, or you modify it based on what you're doing. So this is going to be cont list, so I'm making a list of these contrast vectors here that we created, and then I do least square. I create this least square objects that are the least square means using model 0. So I'm using the same model as before, and I have to specify that power is the treatment variable that contains the treatment levels. And then I create contrast 1 using the contrast function, least square, cont list, and then I'm adjusting for Bonferroni. I could also do CDAC. I don't think none works like it's supposed to. So those two would be possible, and then this is what it prints out. And it tells me that the p-value adjustment is for the Bonferroni method, and there's 3 tests. So it's telling you what R is right here. Okay. And so then I come up and I can say for the contrast, mu3 minus mu4, we test the hypothesis, okay, here, versus the alternative hypothesis. Oops, that should be an H1. Okay. Probably did that everywhere. Yes, I did. So I'll change it now so I don't forget later. That's 1. Okay. Against the alternative, that they're not equal, I give the test statistic with the degrees of freedom and corresponding p-value. Again, if it's less than 0.0001, we put that, we don't put the actual. So therefore, we reject H0, that's our decision, and then our conclusion, there exists sufficient evidence to support the claim that the mean etch rate for a power level of 200 watts is different than that for 220, using a confidence level of, I should say, using a Bonferroni adjusted or experiment-wise confidence level of 95%. The test was performed using n equals 5 observations for each power level, and Bonferroni is capitalized. Okay, and so then I do the same for the others. The other two, and there's two ways to write this one. I showed you in the lecture video that I can write this as the mean of the first two minus the mean of the second two, and it's exactly the same test. You're dividing by 2, the 2's cancel out, and you get it's identical to this test here. Okay, so you can write this up in the two different ways, as the mean of the first two power levels are the same as the mean of the last two, or they're, in this case for the claim, it's that they're different. So again, we failed to reject H0 for this one. Or actually it says failed to reject, but do we? No, we reject, I'm sorry. So this, we reject H0, and there exists sufficient evidence to support the claim that the average mean rate for the power levels 160 and 180 are different from the average of the mean etch rates for power levels 200 and 220 using a Bonferroni adjusted confidence level of 95%. Test performed with n equals 5 observations in each. So when we look at this, the first contrast, here's our estimate of the difference. Here's our standard error. And you'll notice when we have two mu3, mu4, and mu1, mu2, there's only 2 means in there, and so our standard error is exactly the same. But when we have 4 of them, then if you think back to the formula for the standard error, it's different, so it comes out to be larger. And then we've got the t-value, the actual test statistic value right here, and then the p-value that corresponds to it. If you change this from Bonferroni to, let's say, if I say none, where do I do that? Yeah, here. If I change this to none, then watch this value. It's the only one that's going to change because it's not too small to show up. So now it's 0.0064. So that's the only thing. And let's see, -3, that changes 11.86, and this 7, we'll look at that. I'm going to Control Z, rerun this, and so I can look back to what it was. No, those stay the same. So they stay, that's right. So the test statistic value doesn't change, but the cutoff or critical value does. So that changes the p-value. You just can't see the change in this because these two because it's so small. But this one was large enough for us to see the difference, and so it tells us. All right, so this can be used for Bonferroni, CDAC, or for the LSD or unadjusted method. Okay. Since all 3 contrasts are significant, we can calculate the confidence intervals for all 3 of the contrasts. Here we can use the unadjusted probabilities, or we can use the, let's see, why do we use the unadjusted? Okay. And then, oh, and here are the adjusted. So if we want to use the adjusted, so I do both. So here's the unadjusted, and then here are the adjusted. Okay. Now, I didn't write the interpretations for these, but you could copy and paste from up here if you're going to use those. Okay, so again, you would usually only use either the unadjusted, the Bonferroni, or this Chef's method. You wouldn't use all 3 unless it's a homework problem and they ask for all 3. Okay, you might run all 3 on your own when you're exploring this analysis in real life, but you don't want to confuse people, so you usually choose one of them and present it. But it needs to be chosen based on good logic, not just on which one shows you what you want to see. Okay, so that's very dangerous. All right. In this case, there's no issue. All 3 of them say that the differences are significant, so we don't have to worry. But in some cases, one test will say that it's significant, the other will say that it's not. and then the third one might go either way. So you need to determine which one you want to use ahead of time so that you're not biased in your analysis. Okay, that's really important. It's hard to do, but the ethics for research tells us that that's what we're supposed to do, and that is actually in some regulation. So it is important that you follow that. Okay. Since all three contrasts are significant, oh yeah, sorry, I've already read that. So here's the first one. Here's the Bonferroni one. Okay, and then Sheffey's method. So yeah, so let's run Sheffey's method. And then I went over how to write up. So we have the p-values. We have all 6 possible ways to do this. So the experiment-wise, pairwise, 95% pairwise confidence intervals and hypothesis test using Sheffey's method is below. All the pairwise differences are significant at alpha equals 0.05. So if you want to do hypothesis test, then you would remove this line here because this is for the lecture and this is instruction to you, and then you would get rid of anything you're not using down here. If you were reporting confidence intervals, then you would report it like this, and get rid of what's in parentheses. All right. All right, but this is instruction to you. Since these are positive ones, the lower limit does not contain, is not below 0, so it's above 0, and so therefore the interval doesn't contain 0. If they were all negative intervals, then the upper one would need to be below 0 for it not to contain 0, or you could just say they do not contain 0. And then, so there's a couple of different ways to state this. All right. And so that's for the confidence interval reporting, and for reporting specific differences of interest, then we would use something like this. Contains the true mean difference in each, and etch rates between this and this, using sample sizes here. Okay? So I've given you 3 different ways to write this up. All right. So I'm sorry this video took so long, but I wanted to take my time and explain this well so that you have the ability to do your homework and projects the best. You can come back to this video and review something if you need to. Again, I haven't gone through everything, so modifying some of this code is a little tricky, just tedious. And since you don't have a lot of experience with that, come to office hours. I'm happy to walk several of you through it all at once if you like. So again, take care of yourself, stay safe, because we want to see you next time.